Most of the problems we've considered so far have been using either a particle model, where all of our mass is concentrated at one single point at the center of mass, or a rigid body model, where our body does not stretch or squish at all. In reality, though, we know that when you put force on objects, they tend to deform. We have ways of dealing with that, and we're going to learn about that right now: stress and strain. The actual real full material science is a little bit more complicated. There's a fancy mathematical thing called a tensor that you get to use with stress tensors. It's fun stuff. We're just going to get a brief introduction to some of this behavior. So let's say you have an object here, and this object is trying to stretch out. By which I mean we have some length, we pull on it, and it stretches. As long as we have low stress values, which I'll define in just a second, then we say that our stress is going to be equal to our elastic modulus times the strain, which also I'll define in just a second, and maybe should have defined it first. Similarly, if we try and squish this down, we can put this under compression, and it'll squish down a little bit. Both of these things are called normal stress because we're acting normal to the surface there, either stretching it out or squishing it. Stretching it out is called tension, and squishing it is called compression. When you're in tension, you have tensile stress, and this is that stress I was saying I would define. We'll say that our tensile stress is the normal force divided by the cross-sectional area. That means that we apply some force, and then whatever cross-sectional area we have in here, you divide by that. This kind of makes sense. If you have a small little strand of hair, there's a very small cross-sectional area, so a little bit of force will be a lot of stress. But if you have a bunch of hair all braided together to make a rope, then you have a much higher cross-sectional area, so you have less stress on the overall rope because there's more cross-sectional area even with the same force acting. All right, so that's stress. You can put materials under stress in tension by pulling on them, or under compression by trying to squish them. We have tensile strain. That's defined as the fractional change in length, or you pull on it and it increases in length by some delta L, and then you divide that delta L by your original length, so you get a dimensionless measurement of how much this thing is stretching out. We then say that Young's modulus is defined as the ratio of that tensile stress to the tensile strain. You can plug in what these are over here and get another relationship here if you so choose. So rearranging this, we can say that our tensile stress is equal to our elastic modulus, which is Young's modulus, times our strain. There you go. All right. You can test this stuff with materials testers. They're kind of cool. You can actually build one yourself if you'd like, with a lead screw that you kind of turn with your hand, and just get some force sensors of some sort to be able to measure your material properties. That's elastic modulus for Young's modulus with tensile behavior. So that's putting things in tension. What about liquids, though? Let's say that you exert a pressure on something. So a pressure is a force over an area, but you can think about surrounding something with a pressure. I'm thinking about you take an object and you have it at the top of the water, and then you move it down deeper in the water, and it starts getting squished on and compressed some by that change in pressure. We say that our bulk stress is that change in pressure, and our bulk strain is the fractional change in volume as you squish that thing down. Then we can say that our bulk modulus is the ratio of that stress to strain, or our change in pressure over that fractional change in volume. The negative is there because we define it so that our bulk modulus is positive. If you think about it, as the pressure increases, the volume decreases. This way, with the negative, once you plug those in, you'll end up with a positive number coming out for bulk modulus. And then we can define our compressibility as the inverse of our bulk modulus. So that's how that works. You can rearrange this how you'd like, do what you'd like with it. We'll mention one other relationship here. So we've had normal stress. Here we've got some bulk stress. And now we'll talk about shear stress. Shear stress is where you've got some forces that are offset from each other by some distance here, L naught. And this is how shears work, or scissors work. You've got your paper, and you try and put some force offset by a distance, and you move that distance really close to one another to have a very high shear stress there. Shear stress is that shear force divided by the cross-sectional area. And shear strain, gamma, is delta x over L naught, where that delta x is how much you kind of shift over divided by the distance between the application of that force. Then our shear modulus, as with these other moduli, is defined as the stress over the strain. There you go, stress over strain, you can plug stuff through. And so now you can say that my shear stress is equal to my shear modulus times my shear strain. There you go. Stress, strain, and moduli.